Hello everyone and welcome to another lecture related to graphs. This lecture is dedicated to algorithms that find the shortest path from a single source node in a weighted and directed graph. We will begin by first defining the problem statement, followed by proving the optimal substructure of a shortest path. Then we will introduce an important concept called negative weight edges. After that, we will see what is the relaxation technique and how it will be used in the algorithms to find the single source shortest path. The topics covered in this lecture are from chapter 24 of your main reference book. But first, a quick recap of the previous lecture. We studied about minimum spanning trees, or MST, and saw that for the spanning tree to grow gradually, we needed to determine a safe edge in each step that respects the cut. Based on this concept, we saw two simple algorithms, namely Kruskal's algorithm and Prim's algorithm. In Kruskal's algorithm, we sorted the edges according to the increasing order of their weights, and on each iteration, we selected an edge from the sorted sequence if it connected two disjoint tree rooted at the vertices of the graph. On the other hand, Prim's algorithm began from an arbitrary vertex and found the light edge crossing the cut in each step. Both algorithms could be implemented in O E log V time. Finding the shortest path is an optimization problem that is encountered in many tasks more frequently than you can imagine. If you recall, I had briefly introduced this problem in the very beginning of this course, where we wanted to go from NU to MIT biplane in the shortest time. In today's lecture, we consider the graphs to be weighted and directed. The weight function W, given over here, maps each edge to a real value, and WP denotes the weight of some path P that is defined by the set of vertices it covers. So the sum of the weights of the edges in the path P is defined mathematically as shown over here. The weight of the shortest path from U to V is given by delta UV and is defined as the path with the least weight from U to V if V is reachable from U, and infinity if otherwise. So here, W of P would be equal to delta UV. Some may wonder, what does the weight of an edge mean? Depending on the context, edge weights could be distances, time, cost, penalties, or any other metric. Also, the BFS algorithm we saw earlier gives us the shortest path on unweighted graphs. That is, they work on graphs in which all the edges have unit weights. The focus of today's discussion is on single source shortest paths, or SSSP for short. Here, given some weighted directed graph G, we want to find the shortest path from a given source vertex, say S, to every other vertex in the graph. The two algorithms that we will be studying today can be used to solve other forms of SSSP problems. We can use them to find single destination shortest paths where we are interested to know all the shortest paths to a particular destination vertex in the graph. Also, solving the shortest path problem between two specific vertex pairs, and finally, for every UV pair in the graph. The algorithms heavily lean on the fact that a shortest path between two vertices includes other shortest paths within it. So we see that they have an optimal substructure and therefore can be solved using dynamic programming and greedy approaches. Interestingly, we will soon see that the Dijkstra algorithm is greedy in nature, whereas the Floyd-Warshall algorithm that will be covered in the next lecture is a dynamic programming algorithm. The theorem given here formulates the optimal substructure property of a shortest path formally. It states that for a given weighted and directed graph G, if P, which is given over here, is the shortest path from vertex V0 to Vk, then for every I and j values between 0 and k, the subpath Pij will be the shortest path from the vertex Vi to the vertex Vj. The proof is very straightforward. Break down the path P from vertex V0 to Vk into three parts. So we have three subpaths as shown over here, from V0 to Vi, and from Vi to Vj, and from Vj to Vk. So the weight of path P would be the sum of the weights of these three subpaths. Now, assume there is some path Pij naught from Vi to Vj such that the weight of this path is lesser than the weight of the path Pij. This means that there exists a subpath with lesser weight than the subpath of path P. In other words, if I replace Pij with Pij prime, then I should get a shorter path than the path P that we already have. But we know that P is the shortest path between P0 and Pk as assumed at the very beginning in this theorem. So this contradicts our assumption, and thus every subpath of a shortest path is also a shortest path. Sometimes an edge can have a negative weight pertaining on the context. So a shortest path may include edges with negative weights. If the graph contains a negative edge cycle reachable from the source vertex S, then the shortest path weights are not well defined, meaning that there exists no shortest path from vertex S to a vertex on the cycle. Nonetheless, if the graph contains no negative edge cycle reachable from the source vertex S, then the shortest paths are well defined, even if the path includes negative weight edges. To understand this better, let us look at an example next. In this example, we have a partition graph labeled from A to J. In the subgraph on the left, the shortest path from source vertex S to A is obviously 3. The shortest distance from S to B is 3 plus minus 4, which is equal to minus 1. Now let's follow the shortest path from S to C carefully. I can go from S to C by traversing the edge SC once, which would give me 5. I can also go from S to C by traversing the edges SC, CD, and DC, giving me a total of 5 plus 6 minus 3, which is equal to 8. I can keep looping in the cycle as many times as I want, but the shortest distance will always be 5, since every traversal of the cycle keeps adding to the distance between the vertices S and C. So since the cycle has a weight of 6 plus minus 3, which is equal to 3, and it is positive, the shortest path will be the path with no cycles in it. Similarly, I can traverse the cycle given here to go from S to E infinite number of times. But we see that unlike the previous situation, the weight of the cycle is 3 plus minus 6, which is minus 3 and is negative. That means the more I traverse the cycle, the shorter the distance becomes between S and E, which basically would converge to minus infinity. This makes no sense. Therefore, this cycle is called a negative weight cycle and should be avoided in order to have algorithms find proper shortest paths. In the subgraph on the right, none of the three vertices H, I, or J are reachable from S. Therefore, there exists no shortest path from S to any of these vertices. And therefore, the shortest distance from S to all these three vertices would be infinity. Therefore, the interesting question would be, can a shortest path contain a cycle at all? So if the cycle is a negative weight cycle, we saw that it cannot contain it because it reduces the distance from the source to any particular node on that cycle every time you loop the cycle. So therefore, we cannot have a negative weight cycle in the shortest path. How about a positive weight cycle? We saw this as well. A positive weight cycle adds to the distance between two nodes, Therefore, we try to avoid the positive weight cycle as well. Keep in mind that the shortest path from any source to any other vertex would not be necessarily unique in a graph. So there could be more than one shortest path from source node S to any other vertex in the graph as shown in this example. So we see that we can go from S to X through this path, or we could go from S to X using a different path while the weight of the path chosen would be the minimum. Relaxation is a simple technique that the two algorithms for today will be using to test whether a shortest path can be further improved or not. For this purpose, we need to keep track of two attributes for each vertex v in the graph. One is the attribute v dot e, which is an upper bound value or estimate on the weight of a shortest path from S to v. The other attribute is v dot pi, which indicates the vertex through which we arrive at vertex v when determining the shortest path. So basically, during the initialization of the attributes of the vertices in the graph, we set the estimate d to be infinity for all vertices except for S, and we set their predecessors to be nil. In the case of the source vertex S, we set S dot D is equal to 0. What happens in the relaxation of an edge UV with weight W is that it checks if the estimate of vertex V, which is V dot D, is greater than the sum of the estimate value of U and the weight of edge UV. If greater, then it updates V dot D to the sum U dot D plus weight of the edge UV and changes the predecessor of V to U. If not, no changes are made to the attributes of vertex V. So in this example over here, figure A shows us that relaxation occurs because the value of V dot D is 9, which is greater than the sum of 5 plus 2. Therefore, we update this 9 and we replace it with the sum 5 plus 2, which is equal to 7. So we relax this edge. But on the other hand, in figure B, we see that the sum 5 plus 2 is 7, which is greater than 6, and therefore no relaxation takes place on this edge. The first algorithm for finding the single source shortest path is the Bellman-Ford algorithm. The algorithm has a few unique features. It can produce the correct answer if the edges have negative weights, but only if there are no negative weight cycles that are reachable from the source vertex. If it finds a negative weight cycle reachable from the source vertex, it will return false, indicating that there is no solution for this graph. If no negative weight cycle is found, it then returns true and the SSSPs in the graph. Each edge in the Bellman-Ford algorithm is relaxed v minus 1 times, where the absolute value of v is the size of the vertex set. The pseudocode for Bellman-Ford algorithm is shown here. The inputs to this procedure are the graph G, the weight function W, and the source vertex S. On line 1, the graph is initialized according to the initialize single source procedure that we discussed on slide number 9. In the for loop on line 2, every edge in the graph is relaxed using the relaxation technique we just saw. This is repeated v minus 1 times over each edge in the graph. Then, on line 5, the for loop checks to see whether there exists any edge that can be further relaxed or not. If yes, it then returns false, indicating that it could not find an SSSP solution for the graph due to the existence of a negative weight cycle. If no, then it returns a true. The running time of Bellman-Ford algorithm is dominated by the nested for loops on lines 2 and 3, thus taking OVE amount of time to execute. Here is an example where Bellman-Ford has been applied on the given graph. Figure A is a graph after the initialization step on line 1 of the pseudocode. Starting from the source S, we then can list all the edges leaving it and relax them in any order. Note that there is a cycle between vertices T and X, but it is not a negative weight cycle, as the total sum of the cycle is 5 plus minus 2, which is equal to 3, that is positive. The shaded edges indicate that the edge has been relaxed and therefore the predecessor of the vertex V has been updated. Continuing the process at most V minus 1 times, we would finally get the result as shown in figure E. Pay attention that you may not require V minus 1 times to relax each edge, but even much lesser than this. You know that you should stop relaxation when in any two consecutive iterations, no edge is relaxed. Now let's consider a weighted DAG and see what happens when we apply the relaxation technique on it. If we apply DFS on the DAG and topologically sort its vertices, then by relaxing each edge only one time in the sorted order, we can compute the SSSP in theta V plus E time, which is lesser than the running time over a non-DAG that we have seen earlier. Obviously, since there are no cycles in a DAG, shortest paths are well defined. So, topologically sorting the DAG orders the vertices and relaxing each edge that leaves each vertex would result in a linear running time. This is the pseudocode for finding DAG shortest paths. First, we topologically sort the vertices in the DAG. Then, initialize the attributes of each vertex. On line 3, we take each vertex in the sorted order and relax every edge that leaves this vertex. Since it always produces the right answer, it is widely used in determining critical paths in project management. I am sure you all must have taken a course on project management or at least heard of PERT charts. A critical path in a PERT chart is the longest path in the project, which corresponds to the maximum time taken to complete the project. Each edge along the critical path carries a weight which contributes to the total weight of the path. Hence, the weight of a critical path bounds the time taken to complete the entire project. This example shows the DAG shortest path algorithm in action. Starting from figure A, we topologically sort the vertices as given here. We then begin with vertex R and relax the outgoing edge RT once. Since it cannot be relaxed, we move to vertex S and do the same for edges ST and SX. Here, the shaded edges denote the edges that have been relaxed, and the black vertices tell us that the outgoing edges from those vertices have been checked for relaxation. The final SSSP for the DAG is shown in figure G. The second SSSP algorithm is the infamous Dijkstra algorithm. Unlike the Bellman-Ford algorithm, Dijkstra's algorithm solves the SSSP problem on weighted and directed graphs that have non-negative edge weights. That means W of UV is greater than or equal to 0 for each edge UV in the graph. This is how it works. First, we initialize the graph's attributes using the initialize single source procedure seen earlier. Second, we create a set S and initialize it to an empty set. Third, put all the vertices in a min priority queue denoted by Q. Then, while this queue is not empty, we first dequeue the vertex with the least D value and place it in U. Then we add the vertex U to the set S. And finally, for every edge UV leaving U, we relax the edge. As shown in this example, we see that we dequeue the source vertex S first, since S dot D is initialized to 0. We then relax the edges that leave S. that is edges ST and SY. Between vertices T and Y, we have Y with the lower D value, which in this case is 5. So we relax all edges leaving Y. In this figure, the three outgoing edges are YT, YX, and YZ. Now, among vertices T, X, and Z, we see that Z dot D is equal to 7, which is the least value. So we relax all edges leaving vertex Z. We keep doing this until we have visited or dequeued all vertices from the queue. So the final SSSP for this graph is given in figure F. Some food for thought. As exercise 1, apply the Dijkstra's algorithm on this graph, assuming vertex A as the source vertex. In exercise 2, start from vertex A and use Dijkstra's algorithm to find the shortest paths and their weights to vertices G, D, and F.